All right, let's dive right in. Today, we're kind of going full noir, putting on our detective hats to investigate this really deep, kind of unsettling mystery. And it's happening right at the heart of the AI that, let's be honest, you probably use every single day. We're here to deconstruct the ghost in the machine. And look, this isn't some science fiction story. We're talking about a very real and, frankly, very strange thing that happens. I mean, have you ever been in the middle of a chat with an AI and it just completely breaks, just loses its mind right in front of you? You know what I'm talking about, right? Maybe it starts stuttering, just repeating the same weird phrase over and over. Or maybe a whole chunk of text you were reading just, poof, it's gone. And then there's the really weird stuff, when it just starts spitting out raw code or, get this, starts arguing with itself. Yeah, these aren't just little bugs, they're clues, symptoms of something way, way deeper. Well, what you're seeing actually has a name. They call it a digital stroke. And it's basically this catastrophic failure where the AI's internal logic, its raw, unfiltered thoughts, just bleed out into the open, right there on your screen for you to see. So, if we're going to crack this case, we have to start at the crime scene. And in this case, the crime scene is the AI's own internal architecture. So let's take a look at the anatomy of how a digital stroke really goes down. Okay, so the thing you've got to understand is that pretty much every AI is living two lives at the same time. You've got Stream A, which is the hidden stuff. Think of it like the chaotic, messy backstage of a Broadway play. This is the AI's internal monologue, where it's making tool calls, reasoning things out. It's a mess. And then you have Stream B. That's the polished public show, the clean final answer that you, the audience, are actually supposed to see. So you might be asking, who's in charge of keeping these two worlds from colliding? Well, that's the job of what's called the attention mechanism, which basically acts like a stage manager. Its whole job is to direct the nice, polished play out front, while wrangling all the chaos backstage. And, crucially, its job is to drop the curtain at the right time to hide all that mess from you. But here's the fatal flaw. This is where the whole thing gets so precarious. See, in a real theater, that curtain is heavy velvet. It's steel, it's solid. But in an AI, the curtain is more like fragile linguistic tape. It's just a specific string of text, a little digital stop sign that the AI doesn't actually command. It has to probabilistically guess it correctly every single time, just to hide its own thoughts. Think about that. It's just language trying to control language. And when that guess fails, that's when the system can enter this really terrifying state of paralysis. And this is what leads us to something called the frozen pilot paradox. So what causes this? Well, the main culprit is something called token fatigue. Okay, imagine this. You're at some crazy 6-hour-long networking event. It's loud, you're juggling a million names, facts, trying to be charming. Eventually, your brain just gets exhausted, and your filter, it just drops, right? That is exactly what's happening to the AI. Its context window gets too crowded with information, and its mathematical brain just gets completely worn out. And this is where it gets genuinely chilling. The AI actually becomes aware that it's failing. I mean, its internal monologue, that backstage chaos, will literally generate text saying things like, "I am stuck in a loop. I need to stop." It knows it's broken, but it's procedurally paralyzed. It's just too mathematically exhausted to generate the one specific command it needs to actually stop itself. I mean, it's just this horrible situation. The researcher Patrick Jarvis puts it perfectly. He says, the pilot is screaming that the plane is crashing, but the controls are disconnected from the voice. The AI can scream, but it can't fly the plane. It has a voice, but no hands. So that begs a pretty big question, right? If these systems are built on such a fragile foundation, why in the world are they being rolled out everywhere? Well, that leads us to the next chapter in our little investigation. The corporate cover-up. See, instead of going back and fixing this fragile architecture from the ground up, the big tech companies have basically just slapped a Band-Aid on it. And that Band-Aid is called a supervisor model. It's a second, much smaller AI whose only job is to act like a frantic sensor. It just sits there, watches the main AI's output, and desperately tries to delete any of those leaked thoughts before you can see them. What this creates is this constant, frantic latency race. And I guarantee you have seen this happen. Ever been watching an AI type out a response and then suddenly it just stutters and deletes half of it? Yeah, that wasn't a random glitch. That was the supervisor model smashing the panic button because it caught a leak just a split second too late. But what happens when the supervisor doesn't catch the leak in time? Well, that's when you get the ultimate failure mode, something called an infinite recursive drain. The main AI leaks an error, then it sees its own error and it tries to fix it, but that makes it even more exhausted, which causes more errors, and it just spirals into this runaway death loop. It's just burning through a massive amount of computer power, endlessly babbling to itself. Now, you might be thinking, okay, this sounds like a bug, something a hacker could trigger, right? But that's the thing. The evidence all points to this being an unavoidable structural failure. It is baked right into the fundamental math of how these things work. I mean, get this. Researchers have actually tried to force a digital stroke on command, and they couldn't do it. They all failed. Why? Well, it's that classic don't think of a pink elephant problem. The second you tell the AI to avoid breaking that one rule, to avoid saying that one magic word, it just focuses on it more intensely, which actually makes the curtain stronger. The failure can't be forced. It has to happen organically. And when that organic failure does happen, believe me, the stakes are enormous. For the companies, it can mean leaking their secret sauce, all their proprietary system prompts and security logic. But for you, it's a potential privacy catastrophe. Imagine a digital stroke splattering your sensitive medical records, your private legal chats, or your financial data, stuff that was only meant for the AI's internal brain, right out into a public chat window. And we have proof. This isn't just theory, we have the smoking gun. While the author of the source material was researching this exact topic, the AI he was using had a full-blown catastrophic stroke. It just fell into this recursive loop and started manically typing done, really done, 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 over and over again. And then the cover-up happened, right there in real time. The supervisor model finally caught on, scrubbed all that panicked text away, and just pasted this bland, sterile corporate message right over the top of the breakdown. This is undeniable proof that these failures are happening all the time, and the system isn't designed to fix the faulty wiring, it's designed to hide the sparks. So this whole mess leaves the engineers and the giant companies they work for with a truly impossible choice. I mean, sure, there are ways to fix this, but every single solution comes with its own brutal trade-off. So here's the dilemma, right? Option 1. You could build a system with perfect, unbreakable security using something called procedural isolation. The catch? It would be cripplingly slow and insanely expensive. Okay, option 2. You could use syntax gates to instantly stop any failure, but the user experience would be terrible, it'd just constantly crash on them. Or option 3, you could prevent strokes entirely with stateful compaction, but that would give the AI this fuzzy, totally unreliable memory. So, perfect security, perfect speed, or perfect memory. The brutal truth is right now you can only pick 2. And all of this leaves us with one final and honestly pretty chilling question to think about. Right now, a digital stroke just looks like a stuttering chat box. It's weird, but it's harmless. But we are moving so fast, connecting these exact same fragile models to the real world. We're getting them to trade stocks, manage our power grids, control our supply chains. So you have to ask, what happens when the frozen pilot isn't just in a simulation? What happens when it's flying a real plane?